Just gonna wait a couple more minutes before we begin. Just gonna put the slides up. I'm just gonna ask that for the start of the lesson, everybody mutes themselves. And then if you have any questions, feel free to raise your hand, ask in the chat, or unmute and ask. All right. So yeah, we will begin in 1 or 2 minutes. Sorry, can I ask that you please mute yourself? So this is the first week of the TechDreamer lessons, and I will be teaching about computers and programming and anything around that, which is a system, and computers, which are like which are items that we rely so heavily on today. So yeah, I will be teaching about that over the course of the next few weeks. This is week 1, which is what is considered the basics, kind of the building blocks of how computers work and what allows them to work, and how and we'll be learning about binaries as well, which is, I'll go more into it, but a system that computers rely on to basically work and do the everyday tasks that we ask them to do. And this will give us kind of a foundation for the future lessons, which will go a little more in depth to detailed items. Yeah, so just wait 1 more minute and then we can begin. Can everyone see and hear me? If there's any issues, just feel free to let me know in the chat. And I'll also, if everyone has access to the chat, I'll be sending an image, which might help just with binaries. Okay, then I say that we'll begin. Other people can still join, but yeah, we will begin now. So the first thing we will discuss is hardware versus software. So these two are two very crucial parts of what allows a computer to work. Hardware can be simply defined as the physical, tangible components of a computer system. So this can be CPU, memory, storage devices, power, all like the actual physical things that you see. So if you look at a phone or a computer or whatever device you're on the Zoom call right now, the actual metal or plastic that you hold and you click on and you look at is the hardware, such as the screen or the keyboard or any of that, and that would be considered hardware. On the other hand, software, it would represent the more intangible items, such as programs and instructions and data that govern the operation of hardware. What I mean by this is software is what allows you to see something on the screen. So even though the actual screen is hardware and the pixels that light up are hardware, what is shown, and for example, currently what's showing, which is hopefully my screen, is the software and is the code and the programs and the instructions for the hardware. So I want you to think about software simply as a set of instructions. So the code is written, and that is seen, and that's mostly what code is. It's just a set of instructions for what the computer or the hardware should do. Yeah, so does anyone have any questions about that? And then as you can see in these two images over here, so yeah, software is like code, a set of instructions, and hardware is the actual device, the battery, the camera, as you can see in these phones here. Very good. All right. Now we will move on to the next slide, which is computers. So when we think about computers, we often think about like a laptop or something with a mouse and a trackpad and something, that you use to do your work or watch something. But computers are represented by more broad terms. So officially, computers can be defined as an electronic device for storing and processing data. This is typically done in binary form, which we'll discuss more in a couple of slides, which is the instructions given to it to do a certain program. So computers receive instructions in the form of code, which is software, and then they will use those instructions to process data. And that is what that is a simple way to define a computer. So for example, a phone, even though we don't think about a phone as a computer, even though while technically it doesn't have a mouse, a trackpad, or a keyboard, a phone does have a chip and like CPU and memory, which allows it to process data. So for our cases, we're going to consider a phone a computer because it has all the ports that allow it to process data and do all the things that we needed to do, such as watch something, or even though it's a small screen, we can watch something, we can make phone calls, we can send messages and emails, et cetera, et cetera. So for that reason, we will call that computer. Does anyone have any questions about this? Okay, great. Then we'll move on. Okay, so computers at first can seem very complicated. In the top right, you can see a motherboard. And the important way to think about a computer is it has an input and it goes through the processes of what a computer can do, and then that will output something, which is what is shown here. So here I list all the important components to require a computer to work. And while, in this modern world, computers do have a lot of extra hardware, which, can make them work better or look nicer or whatever people want them to do, computers really have about 10 crucial items which they need to work. The first thing, which you've probably heard about before, is a CPU, which stands for Central Processing Unit. A CPU is essential for executing instructions and performing calculations. So you can think about this as like the power of the computing power, right? Central processing unit. This is what processes the data that we discussed before. The next thing is memory, or what can also be called RAM, is at least a small amount of RAM is necessary for temporary data storage while the computer is running. So this isn't like long-term memory, like when you take a photo and it's put onto the memory device. This is just, you ask it to perform an action and it needs to remember the action to maybe, like when you make a Google search, for example, and then you want to click on something within that Google search, it needs to remember its original instruction. So that's how RAM would work. Thirdly, the power supply unit. This would be different than the thing you plug into an outlet. This is more, so there's all these essential components, such as the memory unit or the CPU, and they all need power somehow. So the PSU is what you could call it, would kind of bring power to all these devices. The fourth thing is a motherboard, which can be seen here in the top right, which kind of brings all these components together. So the CPU and the RAM and everything on their own, they don't do much, which is why we're saying these are all important components that when they're brought together and when they're connected using the motherboard is what allows them to process this data and work as a computer. So that's the importance of a motherboard. Fifth, a storage device. A basic storage device is needed to store the operating system and essential files. So this is the storage, like when you take a photo and then it takes up storage on your device. So the first thing that storage devices must have are the operating system, which is what we discussed earlier, which is a software. So the system that allows you to, open a tab of Google Chrome or open a certain program is the operating system. And that's what, turns a computer into just all these parts into something that, a user-friendly thing that can actually be used. And so that will be stored on the storage device along with all the files. So when you when you make a Google search and then you download a file from it, that will go into your storage device. And this can be external or internal, such as an external storage device would be a USB drive or like a hard drive which you plug into your computer. And then internally, you can also have storage which usually are built into computers and just go on to and the default is that I'll go into there. The sixth thing is basic input and output system. So the firmware initializes hardware during startup and loads the operating system. So when you first turn on your computer, you need a system which can basically make it go from a black screen to show something, which would be like, which would be showing your I guess, yeah, what we discussed as software. Thank you. What we discussed as being software. So when you turn on your computer, you need something to kind of power up the software and actually show something, and that's the system that we discussed. And then seventh is a display output. A display output is anything that can display the stuff that's being like the stuff that's being processed, the data that's happening, the Google search that you're making. So a computer obviously alone can process a lot of data, but mostly when computers are used, we need to know what data it's processing. So either an external monitor can be used to connect to it and see what's being processed, or like a laptop, you have a screen built in, and that's also a crucial part. I'm seeing in the chat that people are having issues with me not being loud enough. I'll try to speak louder, but also maybe the volume control on your device that you can increase your volume and you can hear better.
Write something. I don't know where to write now.
Sorry?
I can hear you fine from here.
Okay. Yeah, I'm seeing people are saying it's loud enough, but maybe for the people who are saying that they can't hear me well, if they can if there's a way to turn up their volume, just let me know. You can also leave and rejoin.
I think it's fine now, Julian. You can go on.
Okay. Okay, so now we will discuss binary, which they are, while for humans to understand, they are rather complicated. They are the simplest version of the simplest system that allow a computer to work. So binaries only have two options, 0 or 1, on or off, right? Because the moment you include a third option, that the combination of options makes a whole lot more. So binaries is the simple system that allows all computers to process the data and do a certain set of instructions, and therefore allow a computer to holistically work in the simplest form so that it can work with speed and at the pace that you want it to work. So yes, they're made to be very simple. And so the way it works is computers are made up of many transistors. Transistors are like, think about them like the lights that turn on your screen. And binaries tell them when to go on and when to go off. When the binary value is 0, it means off, and when it's 1, it means on. And there's only those two steps, on or off, because if you add one more, it will become a whole lot complicated and make computers as a whole more complicated to use. When understanding binaries, has anyone ever here heard of like a gigabyte or megabyte, like storing photos? So this is the same system, but a whole lot smaller. So when understanding binary, we need to understand bits and bytes. A bit is a smaller version of a byte. So in every byte, there are 8 bits. I know it's complicated because it's similar, but I hope you can see it here. Here I'm circling bits, and here I'm circling byte. It's spelled with a Y, okay? And one bit represents an option of either 0 or 1. So for the case of this lesson, I'm going to use light bulbs, okay? At the top, we can see here, the light bulb off represents 0, and the light bulb on represents 1. And this whole option for on and off is 1 bit. And 8 of those bits creates 1 byte. Now, to show any character, which we will get in soon, takes 1 byte, because you need 8 options of on or off to show any character, color, letter, or number, which we'll get into more later. So yeah, 0 and 1s can translate simply to numbers, and there's a chart, which I will show below, and then I will show how to use it. So as you can see here, both uppercase and lowercase letters can be represented by numbers, which are created by binaries. So for example, here you can see a capital A is represented by 65. A lowercase g is 103. And all these numbers are made, sorry? All these numbers are made with combinations of 0 or 1s, which I will get into in the next slide. And they allow numbers or letters or images or colors or symbols to be shown on a computer at all. Sorry, do you have a question? Or... Okay, then we'll move on to the next slide. So here, this is 1 byte, okay? It is 8 bits, which is 8 light bulbs, which we are using to represent a 0 or a 1. So in this case, every light bulb has a value of 0 because they're all off. And there's 8 light bulbs, which is 8 bits, or what we will call 1 byte. So this is how I would represent it. Now, it's important to think about what makes binary so efficient and the combination of them. So these are just 3 bits, which is less than a byte, and a very, very small amount of storage.
You want to know how to get into this.
Now, having such a small, even though we have such a small value or amount of data, which is only 3 bits, we can do so much with it. So here we can represent 0, for example, because they're all off. Now, with these same 3 bulbs, we can represent 1, with 1 bulb being on, okay? Now, with these same bulbs, we can represent 2, okay? Now, we're still using these bulbs, so now with 3 bulbs, we've already represented 0, 1, and 2, which is 3, right, with 3 bulbs. So currently they're 1 for 1. But now we can keep going. We can represent 3. So now we've represented 4 numbers with 3 bulbs. So 3 bits, which is a very, very small amount, we've already represented 0, 1, 2, and 3. It's a very small amount of data. But now we can keep going. We can count to 4. We can count to 5. We can count to 5, 6, and 7. Okay, so sorry, I went through that a little bit quickly. I'll read start. So we have 0, we have 1, we have 2, we have 3, 4, 5, and 6. So as we can see, just like that, we can with just 3 bits, which is 3 options between on or off, we can do all that counting. Imagine that. We can represent as many as 7 numbers. We went from 1 to 6 and also 0. So with just 3 bits, 3 light bulbs, we were able to represent 7 numbers, which is why, as we can see in the chart, we are able to use the same system to represent all of this. James, do you have a question, or I think you have some background?
Why you call it laugh? I did like. Why you call it laugh? Why you call it laugh?
Does someone have a question? I don't think so. I think you can just go on, Julian.
Okay. It's hard to hear, but okay. So we will now keep going. So if we wanted the number 3 as an output,
May I make a suggestion? People can also put their questions into the chat.
yes. Oh, we have a request in the chat to go a little bit backwards on the bits thing.
If you
Okay.
could just repeat the bits.
Yes. It's very complicated and I went through it very quickly. Do you have a specific question about it, or I'll go through it, of course, again. But if you have a specific question, feel free to ask. Okay. So here's the understanding I'm trying to create. 1 second. Oh, please hold while I type it. Okay. Yes, I will hold. I can send notes on this material if that would help anybody. I can send after the lesson, I can send notes on this material. But yes, I will hold. So, or I'll just explain as well. So below is 1 byte, and 1 byte, as I've said before, will be represented. 1 byte will be represented by 8 bits, and 1 bit is an option between either 0 or 1, on or off. Okay, so here are 8 bulbs, 1, 2, 3, 4, 5, 6, 7, 8, and they're all off. So we currently have 1 byte, which is still a very small amount of data, because when we measure, remember we use mega and gigabytes, which is like hundreds and thousands of these. Okay, but here we have just 1 byte, which all have a value of 0 because they are all off. Now, in the next slide, we have just 3 bits, which is not even 1 byte, because remember there's 8 bits in a byte. Okay, so we have 3 bits. Now, each of these bits, which we are using light bulbs for, have a value of 0, because this one is off. Can you guys see my mouse? Yeah. Okay, so this one is off, this one is off, and
Yes,
this.
we can see your mouse.
Okay, so now, even though we only have 3 bits, 3 light bulbs, we can count 7 numbers, which is why they were so efficient. They are a very small amount of data to store, but they can represent so much more than their own size. Now, so what I was showing is that with the same 3 bulbs, we can show 1. Okay, so this is 1, because this is on, this is off, and this is off. Now, using the same 3 bits, we can show 2, and we can show 3. So now with 3 bits, we've shown when they're all off, which is 0, and then we've shown when the first one is on, which is 1. We've shown when the second one is on, which is 2, and we've shown when the third one is on, which is 3. So now already, just with these 3 bulbs, we've shown 0, 1, 2, and 3. Now, we can keep going because we've only lit 1 of each. So we can say that if we light 2 light bulbs, that will be 4. And if we light these 2, that will be 5. Right? And then we still have the option to light all 3. So we can say that is 6. So now, just like that, with 3 bits, a very, very small amount of data to store, which is this whole system that computers rely on, we have gone from 0 to 6. So we have counted 7 numbers. And that is why computers use these, because you can represent so much with so little, and process this with speed. Yeah, I'm seeing in the chat. Exactly. So, someone has, if you guys can see the chat, someone has said 0, 0, 1, 0, 1, 0, 1, 0, 0. So the zeros would represent the off. So 0, 0, 1 would be off, off, on. 0, 1, 0 would be on, off. I mean, off, on, off. And 1, 0, 0 would be on, off, off, which each represent different numbers. Now, does that make sense to everybody? If you have any questions, or just let me know in the chat, but that's good for everybody. Yes. Okay, very good. Now we will move on. So we will begin with representing numbers with binaries, okay? I know this looks very complicated, but I will explain it all. Second, same thing. Yes, I'm glad everyone's got it. Yeah, I'll also move a little bit slower, if that helps. So let's say we want to use binaries. So this system that we just made up was as an example, right? To show that with just 3 light bulbs, we can show so much. But now I'm going to explain how binaries are actually used by computers. So let's say we wanted to show the value of 3, right? Whatever 3 is, whatever symbol, whatever letter, whatever is represented by it, we want to show 3. Here's how we will do it. Each light bulb, you have 8 bits in a byte. So first of all, you get up to 8 bits. You get 1 byte to represent anything. So here at the very bottom, we have 8 bulbs. 2, 4, 6, 8. Okay, so we can turn on or off any of these to represent something. Now, the first bulb will represent a 1. Okay, and from there, the next bulbs, please let me know if you have any questions about this. The next bulbs onwards will be a multiple of 2 from the last one, which means if the first bulb represents a 1, then the next one represents a 2, because 1 times 2 is 2. That means the next one will be valued at 4, because 2 times 2 is 4. Then times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, and times 2 is 128. Does that make sense to everybody? Each light bulb, each value of 0 or 1 is valued double the last one, and the first one starts at 1. I'll just check the chat now if there are any questions about that, because I just said a lot. Okay, it's making sense. Oh, someone's asking me to hold on. Would you like me to explain it? Oh, didn't understand. Okay. Yes, I will. Of course, I'll explain it again. So, do you understand that we have 1 byte here? You understand that part? All right. Yeah, I'll explain it again. Okay, so we have 1 byte because we have 8 light bulbs. Now, each light bulb needs a value in order for us to represent certain characters, letters, to represent anything. We need to first value each light bulb in a byte. So I'm going to start by saying that any character, any number, any color even, we can represent using 1 byte, which is 8 of these light bulbs. So the first one will be valued at 1. Okay.
I think there was some confusion about why it's getting squared, Julian. Can you explain that?
What do you mean by
Or not, like, why is it multiplying?
Each time it's multiplying by 2, correct. Because in order to show every number on a byte, we can't just value each one at 1 or 2, right? Because let's say we valued each at 2, the maximum we could get to is 2, 4, 6, 8, 10, 12, 14, 16. And there's some numbers that based on the chart, we can see, we need to get as high as 127. We need to get to 95. So we use the system to have both even numbers to get us high and odd numbers to get us to very precise numbers to use the smallest amount of data, which is 1 byte, to represent as much as possible. And in this case, 1 byte can represent anything. Does that make sense? So the first bulb will represent a 1, and then yes, it will multiply by 2 each time. Now, let's say we wanted to get 3, okay? We wanted 3 as our output. We would turn on the first 2 bulbs because the first bulb has a value of 1 and the second bulb has a value of 2. This means that if we, instead of making zeros, yes, just looking at the chat, let me know if you have any questions. So instead of making zeros, or putting zeros which these are, where they're all off, we would have 1 to represent that they're on. And that means if the light bulb that corresponds to 2 and the light bulb that corresponds to 1 are both on, those values would be added together and we would get 3. And that's how we would get 3 as our output. Now, let's say we wanted to get 44. How would we do that? We would turn on the light bulb for 32, so we put a 1 there, the third light bulb. We would put a 1 over 8. 32 plus 8 is 40, so we need 4 more, and we would put a 1 over for the light bulb that corresponds to 4. So now we have 3 light bulbs on, and just with turning on 3 light bulbs, we've represented such a large number, and that is why you square them, instead of just having them each valued at 1 or 2. Because with just turning on 3 light bulbs, which is very little amount of work for a computer to do, you can represent such a large number. Okay. Let me move to the next slide. Now, using base 2 counter. Now, using letters, for example, I'm going to explain how we can use binaries to write, let's say, hi, both lowercase, okay? So based on the chart I've shown, I've taken a snippet from the chart for the H and the I. And the H is 104, and the I is 105. Now, that means we need to represent 104 using binaries and 105 using binaries. To do so is shown below. So 104 would look like this: 0, 0, 0, 1, 0, 1, 1, 0. That means we would do, it would be 8 plus 32, which is 40, plus 64, which gets us to 104. So see, when we add all those values, just by turning on a light bulb, it means that value is added. We can get such a large number, like 104. So that 104, as you can see on this chart that I showed, we get H. Now, to get I, we just need the same thing, except plus 1. Okay, someone is saying they're confused. Which part are you confused by? Would you like to unmute and explain what you're confused by?
Yes, please go ahead and say it.
I know it's a complicated topic.
Okay, it's about the binaries. How come you were able to get 104 with 011010000 and you're able to get 104? How did you join them? How did you add them together? Were you able to sum them up?
Yes. So, do you see 128, 64, 32, 16, 8, 4, 2, and 1? Do you see that?
Yes, I do.
Yes. So this is 8 bits, and each bit we increase by 2.
Okay.
And in order to get such a big number, you need to turn on the light bulb or make it a 1 for that value. You understand? You still understand?
So when turning on the bulb, are you still to multiply by 2? Are you still to square it up, or there's any additional number to?
There's no additional number.
To the...
So for example, we turn on the 4th bulb, right? So what is the value of the fourth bulb?
Pointer to the fourth.
The value of the fourth bulb is 8.
Yes. And then we also turn on the 1, 2, 3, 4, 5. We turn on the sixth bulb. What is the value of the sixth bulb?
32.
The value of the sixth bulb is 32.
Yes. And then the seventh bulb. What is the value of the seventh bulb?
64.
Yes. And now when we add all those together, which I have done here, what do we get? What do we get when
Oh,
we add
okay,
them
I
together?
understand. Thank you.
Yes, we get 104, which is what we have, which is what so it's called the ASC2, which is how all people who do code or do technology or like create these programs have agreed on these values. So it's the chart that I showed earlier. And they have agreed that a lowercase h will be 104 and a lowercase I will be 105. So to show those two, it would be like this. Now, in the next slide, yes, I'm glad people are understanding. In the next slide, we will show this with light bulbs. Okay, just to make it a little simpler. So, there's actually a mistake here. But there needs to be one more light bulb here, and then the third light bulb will be lit up. One will be off, and then 2 more will be on. Yes, I'm glad people are understanding now. And then, so that will be the H. And then for the I, there will be 1 light bulb on, 2 off, 1 light bulb on, 1 off, and then 2 on and 1 off. And that corresponds to this addition here and these values of 0 and 1. Of course, a computer can't represent everything in light bulbs. They just represent in 0 or 1 because it's a very small way for it to process the data, which makes it easy and quick and efficient and allows computers to work and quickly process data how they do. Okay, move to the next slide. Now, so as we saw in the chart, I'll show it one more time. So this is a chart where we got the H and the I, right? So 104 is H and 105 is I. And this is a system called the ASC2, which is how lots of people agree that they're going to use binaries to represent. But the only thing, we represent so much more than just characters, numbers, and letters when we use a computer. So let's say you're texting and you use an emoji, and the color of a yellow face when you make an emoji. How do you represent that color? This is what I will explain now. So, showing images or showing color, it uses a system called RGB, which stands for red, green, blue. And it uses binaries to decide on a certain value of each color. And when those are mixed together, it makes your final color. So can everybody see this yellow color over here? Let's say this is the color of our emoji. To get this color, they put 72, a value of 72 of red, mix that with a value of 73 green, and mix that with a value of 33 blue. And to get all these numbers, 72, 73, and 33, binaries were used. Just like we used binaries to make an H and an I, and we used binaries to make a 3.
Can you explain that just one more time? So to get to the 72, to get to the red color, you had to use
Binaries.
Did they just decide that 72 represents red?
No.
Okay.
72 just decides how much red. Okay, so that will be shown here. So as you can see, the 1 here in the very top left, there's 0 of each, which means there will be no color, which means it will be black. But for example, red, number 3, which is the most of red and none of the others, will give you a pure red. So the max you can get with 1 byte with 0 bulbs, where it counts by 2 each time, is 255. So out of 255, the binaries represent how much of each color will be added to the final mix. So 72 out of 255 is how much red will be added. 73 out of 255 is how much green, and et cetera, which will get us with the final color of this. Does that make sense? If there's any questions in the chat? Fortune, I see you have a question. Would you like to unmute and ask a question?
Has a number. So each color has a number.
I'm asking if the 72 is a constant number for the red, or is there any way it's being calculated?
I'm sorry, I think there's some background noise. Could you repeat your question?
I said, is 72 a number for the red, or is it being calculated in another way?
Okay. So the max value we can make with binaries is
No,
200.
the question, Julian, the question was, is 72 a constant number for the red, or has it been calculated in another way?
Yes. So as we can see here, the maximum value we can make with binaries is 255 if we add these all together. So 128 plus 64 plus 32 plus 16, that will get 255, which means the color here, which the binaries show, will be calculated out of 275. So think about it as like a percent or fraction.
255.
Okay, so 72 out of 255 is how much red you will have. 73 out of 255 is how much green. So 72 does not correspond to red. The 72 just corresponds to how much red, which gets us this final color here. Okay, maybe the next chart will make more sense. As we can see, the 3, for example, in the very top left, if we have 0 blue and 0 green and the max 255 of red, that will get us just red. But if we have, for example, number 47, where my mouse is, we have 102, which is quite a bit of red, also quite a bit of green, and even more blue, we get this kind of purplish color. So it's not, so the 72 here and the 73 and the 33 do not correspond to the color. However, they correspond to how much of that color. Does that make more sense? Okay, thank you, Fortune. Are there any other questions? Yeah, I'm glad. Yeah, this is very confusing. That's why I wanted to, yeah, it's, this is how computers work. So it's a nice thing to know, but it's very confusing. But it will be a strong basis for a lot of the things we do in future classes. Clara Pessu, yes. If you would like, if you have a question.
So there was a screen where you went back to and you said 128 and 64 makes 255. Did I get that right?
I'm sorry, your sound is cutting in and out. But if your question was that if it's out of 72 to make 55, and that's 55.
Now, mention the highest something you could get, the sum of 128 and 64 makes 255, but is that right, or missing something, or is it the sum? So you know where you've got all the 8 bits.
Oh yes, I'll 1 second. I'll move back to that slide. So here, so yes, it's the sum of all these makes 255.
Oh, right. Cool, I
Right.
got it now.
So since the max value you can get with binaries is 255, the colors that everyone has decided will be out of the max value. So you know when we do percent, it's out of 100. Here it's
Yeah,
out of
fraction.
255. So if we have 255 red out of 255, there will be just red. There will be a lot of red, right? But since here there's only a little bit of red, we can see the final color we get doesn't have much red in it.
That's fine. Thank you.
Yes. So yes, the next chart shows 255.
Julian, can you read the last chat and see if that's correct, what Chukwuji is saying?
Yes. What it's trying to say is that we are mixing colors, red, green, and blue. Exactly. So it's a system called RGB. Using 72 part of red from 255 max red color with 73 part green with 255 max green color and 33 parts blue from 255 max. Exactly. So 255 is the max for all of them. And then you're mixing all these parts to have certain amount of each to create a color. So that's exactly that's exactly how we would see it. In this chart on the left, we can see that being put to use. So out of 255, we see some colors where the red has a 255, and then we see that color is much redder. For example, this hot pink, 226 in the bottom left, we see that the red has a value of 255. Sorry. And that means that there was a lot of red in that mix, and therefore that color will come across to look more like that.
So
Good.
Julian, all the colors are made with R, G, and B.
Yes,
Red, green, and blue.
yes,
Okay.
yes. Okay. To Dizzy has a question. I'm just gonna say it out loud. Because yeah. My question is, how did you get the 255 for colors? I thought it was for only letters. Like, I mean, it represents the letters. Okay. Yes, this is a very good question. So the binary system is very well, for us it's very complicated to understand. The fact that it only has two options, like 0 and 1, make it very easy for computers to use, which means computers are going to use it for everything because they can do it quickly and easily without much power. So while yes, binary will be used to represent numbers and letters and characters and whatever else was on that chart that I can put up right now. Sorry. See, so there'll be numbers and letters and symbols and everything. Binary will also be used for many other things, like color, like images. Okay? So imagine you're trying to show an image imagine you're trying to show an image of your dog, right? Each pixel on your screen will be lit up with a certain amount of red, a certain amount of green, and a certain amount of blue, which will be decided by this binary. And when each pixel is put together and you have thousands of these pixels, that will result in an image of your dog. Does that make more sense? So let's say like your current screen right now, where it says, where it's showing all the colors, each little pixel, which is a little like light bulb on your screen. So imagine your screen having 3 light bulbs, one with red, one with green, and one with blue. Each light bulb will light up a certain amount based on how much its binary value tells it to, and then it will result in a final color. And when you have hundreds of these pixels, each lighting up with their colors, it will create an image. So this is how a screen creates images. It also uses the binary system. So this is why the binary system is so important, because it's not only used to show numbers and letters, but it's also used to make images and make colors. And anything you ever see on your screen is just this red, green, and blue, these pixels lighting up, and the binary value out of 255 representing how much of that color should be there. Okay, that's making sense. So yes, that is our final slide. That's all the information we will go over today. I hope that everybody I'm sorry it was a little bit complicated, but I hope that everybody kind of got an understanding of the binary system. It's quite important for the future because it goes into this deeper idea of programming and coding and how computers take what you write as code and because they do everything via binaries. So it's very important to understand that while humans write code in letter form and with words and letters, when a computer reads that, it sees a bunch of zeros and ones, and it takes these instructions, which is how we will understand code in the future class. It takes these instructions that you are writing as words and see them as a bunch of zero and ones. And it does everything with the system because of how simple it is. A byte is a very, very small amount of storage for a computer to process, to store. So the fact that it can do so much with, even like we discussed, it can show 7 different letters with less than a byte, with 3 bits. The fact that it can do so much means that a computer wants to use as much as it possibly can using binaries, including numbers, letters, and even showing colors and images. So yes, I hope that makes sense to everybody. Does anybody have any questions about anything at all in the lesson? Yes.
Yes, I do have a question. Okay, my question is not about this particular slide. It's about a certain slide. Can you please go a little bit backwards?
Backwards. Yes.
Yeah.
More?
No, backwards on the slides.
Forward.
No, go. Yeah, please go. Keep going. Please go. Yes, yeah. Okay, so no, please go a little bit forward. No, not this one. Forward.
Here?
No, not this one. Not this one. Not this one. After this one, I think. Yes, this one.
Yes.
Thank you. It's about not this slide, the one before this slide, please.
This one?
Yes, this one. Yes,
Sorry.
yes, this one. So when you were showing us this particular chart in form of colors, that one was understandable, but this particular one is kind of confusing. Now, looking at 0, it shows NUL, and you said to get H, we need 72 bits to get H and 73 to get I for HI.
Yeah.
So looking at these ones, NUL, you said 0. So are you saying, I just want to know how they're able to get these numbers, what we really need to do to get all these numbers to know which particular one we need to use to get a certain letter.
Yes. So this chart is a system that that just everyone has agreed on, right? So for example, if we want to say hi with an exclamation mark and a capital H and a capital I, right? Here, let me see if I can show you what I mean. So if we wanted to say like this, capital H, capital I with an exclamation mark, right? We would say 72, 73, and 33. Okay? That's not what we would say, but that's what how a computer would read it. So while it's not important for humans to actually be able to do this process, it's important to understand that when we insert this into a computer, really how a computer takes that is when a computer sees that, it reads 72, 73, and 33. 73.
I'm sorry, can I just rephrase my question? This is not my question. My question is, how do they get this 72?
Oh, so how
come
did
up
we
with those
start in the
numbers?
first place?
What did you say?
Are you asking how we made this chart in the first place?
Hello?
Yes.
Hello? Sorry,
Yes.
can you come again? What did you say?
Are you asking how this chart was made in the first place?
I didn't get you. Can you please come again with the question?
Yes. So if you were asking how this chart was created in the first place, how we in the first place decided that an X would be 88 and a I would be 105. Is that what you're asking?
Yes.
Okay.
That was what I'm asking.
So this chart is called the ASCII values, which means that it is a set of values that everyone has agreed on. So all coders, all programmers, all So if you want to be able to integrate your code and your program into something else, you need to agree on a value for binaries. So to make that easier, everybody has just agreed on one system, one set of binaries that will all equal the same value. And this is the system they have agreed on. So this is just a standardized chart, just like people can agree with Roman numerals or anything like that. This is just a standardized chart that everyone has agreed on to allow for programming and technological integration to be made easier. Does that make more sense?
In other words, the chart is constant. The figures on the chart is constant. Is it?
Sorry, could you it's very quiet. I can't hear and you have some background noise. Could you repeat your question?
Are you saying that the chart is constant? The
Yes.
figures on the
Yes.
chart is constant then. Okay.
Yes, so the chart is a decided constant. I'll also write it in the chat, but the chart is a kind of a decided constant that many programmers and technological innovators have decided on to allow for, like, because if let's say one person decides that 57 will be an I, and here they think that 57 should be a 9. You can't those two values have different meanings, so they can't be integrated, because then in one place you'll see a 9 and in one place you'll see a percent sign. So everyone's just decided that it's easier to just have one chart that everyone can agree on, that no matter what, 57 will be 9, a 40 will be an open parentheses, 104 will be a lowercase h, 125 will be a curly bracket, right? And everybody has agreed on these values. Okay. Yeah, I wrote it in the chat. Does anyone have any other questions? Okay. Well, I'm glad everyone understands these ideas. In the next class, since this is a very important but also complicated for us to understand idea, I'll do a slight recap on it, but this is kind of the deep delve that we'll be taking into it. So I see one more question in the chat, which I'll answer in a moment, but I hope that everybody understands the ideas, and I'll answer the question. So in a case where one has to use binary as fast as possible, then one needs to have the chart handy. Okay, so binaries is a system that computers use because, right, it uses zeros and ones, which is very simple for a computer. But for humans, it doesn't take any more work to say hello than it does to say each binary for the H, for the E, for the L, for the L, for the O, and for the period. So when humans actually speak and write, we use actual letters and words. So binaries are just an important idea to understand because it's how computers work, but it's a system that you as a human will never have to use. And it's a system that when you're coding, and even though you're coding and giving a computer instructions, you will write in the form of letters and words, and then you will use a certain integrated coding system or coding line of code that will turn all of your code into just many binaries. So if you make a code that says like open this screen when this button is clicked, that whole line will become thousands and thousands of zeros and ones for the computer, because it's much easier for a computer to look at on off on off on off 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 on than to see like 26 different letters and all these different numbers. So for you as a human, you'll never need to know the binary system, thankfully, because it is very complicated. Yes, you have your hand raised. Do you have another question? Okay.
Julian, maybe you want to just tell everyone a little bit about yourself and you know, your background and stuff like that, just so you can fully introduce yourself.
Okay. Yes, I'm Julian, and I'm very interested in like technology and computer science, and have recently been taking an online computer science course and to kind of learn more about programming languages. But my passion and interest in technology has kind of wanted me to kind of inspire and teach others. So yeah. If there's no more questions, then that's it for today. And if you do have any questions, feel free to stay behind and ask them. Yes, you have a question?
Yes, I do have a question. In this chart here, it said, as you see, both uppercase and lowercase letters can be represented by numbers which are created with binaries. So using binaries like zeros and ones, when you write H with 72, you don't particularly know if you're writing in capital letter, in uppercase or in lowercase. So how do you write binaries in, how do you write letters with binaries in lower cases and in upper cases? How do you know which you're writing?
Yes. So I don't know if you can see, but the value for a capital H is 72. Okay. And the value for lowercase h is 104.
I'm off the thing.
Can you see that? So here is a capital H and here is a lowercase h. So you know they're different. One is big or one is small, uppercase or lowercase, because they have different binary values. So here it's, if you want to represent an uppercase, you would say 72. And if you want to represent a lowercase, you would see 104. Okay, I'm glad I was able to answer all your questions. And I hope everybody enjoyed this class, and that is all I have.
You're welcome to speak up. If anyone has any additional questions, you're welcome to just unmute yourself and speak up. You don't have to use the chat.
Yes. And if anyone has any, let's see, if anyone has any questions or didn't understand anything, there'll be a recording of this lesson on.
I put it. Is it mute? Can you hear us, Julian?
Yes, yes.
Julian, can you show us how that 72, how you add up to 72 to get H?
Yes, so it would be the same system that is used here. So here for a lowercase h, we want 104. So we add 64 to 32 to 8 and get 104. To get 72, we would add 64 to 8, which means we would turn off the 1 bulb, the 2 bulb, and the 4 bulb. We would turn on the 8 bulb, so we would put a 1 here.
Yes.
We would turn off the 16,
Yes.
the 16 and 32 bulb. We would turn on the 1 bulb, the 64 bulb, and turn off the 128. So how it would look for 72 to get H, we would have 0, 0, 0, 0, 0, 0, 0, sorry, 0, 0, 0, 1, 0, 0, 1, 0. And the ones represent that you add them together. And 64 plus 8 is 72.
Thank you.
Yes, of course. Yeah, so if you have any other questions, feel free to speak up. And if you ever want to, if you have any confusion, there'll be a recording of this class on the TechDreamers channel, which you can find at TechDreamers 404. And if you have any questions, feel free here. I'll send the notes, but if you have any other questions, you can reach me at julian@techdreamers.net. So feel free to email me if you have any questions. That's my email over there. And I look forward to seeing you in the next lesson.
Thank you, Julian.
Yes, of course.
It was
Thank you very
excellent.
much.
Thank you.
I learned a
Thank you
lot.
very much.
Yes, of course. If you have any
Thank you
questions,
so
or any
much,
questions,
Julian.
Thank you, thank you.
Julian at
Thank you very much,
TechDreamers.
Julian. We're glad.
Okay. Goodbye, everybody.
Thank you very much. Thank you very much.
Thank you so much.
Thank you.
Thank you. Thank you so much.
Of course.
Thank you, Julian. Thank you so much. That's a great one.
Thank you.
Thank you.
Yes, of course. Bye, everybody. Hopefully see you next week, the next lesson.
Thanks, Julian. Thank you much. Bye.
Bye.
Thank you.
Thank you.
Thank you very much. Yeah, good day.
Thank you so much. Thank you.
Yes, of course. Okay.
Thank you.
Everybody.
Thank you so much. I'm grateful.